Yes, let's look at this question number 2. A gas stream containing a valuable hydrocarbon with molecular weight 44 is to be scrubbed with a non-volatile oil with molecular weight 300 in a tower packed with 1-inch rasking rings. The entering gas analysis has 20 more percent hydrocarbon. And 95% of this hydrocarbon is to be recovered. The gas stream enters the column at 5,000 kg per hour meter squared. And hydrocarbon free oil enters the top at 10,000 kg per hour meter squared. Determine the number of transfer units. Determine the number of transfer units. The equilibrium data is as given below. So this is the equilibrium data. I'm going to have X for liquid phase, and I'm going to have Y for gaseous phase. This I'm going to start here at 0 for X. Y is 0. At 0.01 Y is at 0.1 Y is 0.01. At 0.2 Y is 0.0275. At 0.3 Y is 0.0525. At 0.4 Y is 0.1. Then at 0.5 Y is 0.175. So this is the equilibrium data. With this we can easily quickly plot the equilibrium curve. Then we are now going to solve to get the operating line so that we can plot it as well. So for that we can say solution: gas absorption involves diffusion through a stationary component and the appropriate equation for the determination of the number of transfer units is NOG equal to the integral with limit y2 y1 1 minus y ln all over 1 minus y bracket 1 the equilibrium y minus y dy. So this is the general equation used in determining the number of transfer units for gas absorption. So having noted this, we can now easily say that to evaluate the integral, comma, we need to know the limits. We need to know the limits, very important, of integration. And those limits are y1 and y2. Now, what is the basics of our calculation? We're going to take the basis of 1 pound mole of entering gas. That's the basis we take. So that when we say solute free gas in, it's going to give us 0.8 times 29, and we know that 29 is the molecular weight for air, which will give us 23.2 pounds. We'll now say hydrocarbon, we already know it's 20%, so it's 0.2. That's why when you subtracted 1 minus 0, well, the basis is 1, so 1 minus 0.2 gave us this 0.8. So for the hydrocarbon, we have 0.2 times 44, which will give us 8.8 pounds. So that when we now calculate the average molecular weight of gas, total gas, both the air and the hydrocarbon, we'll now have this plus the 23.2 plus 8.8, we have 32.0 pounds. So that when we now say total molar gas rates entering the bottom of the absorber, V is going to be 500 all over 32, which will give us 156.25 pound moles per hour feet squared. So that's what we're going to have. So if we go further in this calculation, we say solute free gas in is equal to solute free gas out, which is actually 0.8 pound moles per mole gas in. And we can also say that hydrocarbon out is equal to 5. We already know 95 from the 95% that we have from the equation. 5 over 100 times 0.2 of the hydrocarbon in. This will give us 0.05 times 0.2, which will give us 0.01 pound moles. So therefore Y2 is equal to mole of hydrocarbon all over mole hydrocarbon plus mole air, which will give us 0.01 all over 0.01 plus 0.8, which is equal to 0.01235. So with this, we can now find VI to be equal to V2 bracket 1 minus Y2. So in essence, V2, the subject of the formula, will give us V prime all over 1 minus Y2, which will give us 80 all over 100 times 156.25 all over 1 minus 0.01235. This will give us 0.8 times 156.25 all over 1 minus 0.0123, which will finally give us 126.6 pound mole per hour feet squared. So now we're going to have V prime to be equal to 156.25 times 0.8, which is equal to 125. Now for the oil, L2 is equal to 10,000, the liquid rate, over 300, which is 33.3 pound mole per hour feet squared, and XO is equal to 0. Now if we calculate the pound mole of hydrocarbon in exit oil, it's going to give us 0.95 times 0.2, which is 0.2 minus 0.01, which will give us 0.19 mole per mole gas in, so that the hydrocarbon in exit oil is equal to 0.19 times 156.2, which is equal to 29.7 pound moles. Also, if we calculate the solute free oil, it's going to give us, we already know it's 33.3 pound moles, so that the total moles will be equal to this 29.7 plus 33.3, which will give us 63.0, so that X1 will now be equal to 29.7 all over 63, which will give us 0.472. Now if we do a summary of the material balance, following this sketch where we have this, we have the V1 156.2 and Y 0.2. This is the entering gas, this is the leaving liquid. We have L1 equals to 63.0, X1 equals to 0.472 from our calculation. We have the leaving gas as V2 equal to 126.6 and Y2 equal to 0.0124. We have the entering liquid L2 equal to 33.3 and S2 equal to 0. So if you make a material balance from the top bottom to any point intermediate in this tower, we're going to have V1 Y1 plus LX to be equal to V Y plus L1 X1. This equation must be written in terms of the non-diffusion component, and if you write it in terms of non-diffusion component, we have V prime to be equal to V bracket 1 minus Y. Taking this as equation B, we take this one as equation A. Now L prime is equal to L bracket 1 minus X, taking this as equation C. Now if you make this material balance and you substitute equations B and C into equation A, we are going to have that V prime bracket y1 over 1 minus y1 plus L prime into bracket x over 1 minus x is equal to V prime into bracket y over 1 minus y plus L prime into bracket x all over 1 minus x1. So that's what we are going to have as our equation D. Now, having this, we can equate equation D is valid for the column. Now, substituting the actual values that we have into that equation D, we can now have that 125 into bracket 0.2 all over 0.8 plus 33.3. we already found this value from our previous calculations, to bracket x all over 1 minus x equal to 125 bracket y all over 1 minus y plus 33.3 into bracket 0.472 all over 0.528. Now we have that V prime is equal to 156.25 times 0.8, which is equal to 125, and L is equal to 33.3. Solving this equation down, we now have that x all over 1 minus x is equal to 3.79 brackets y all over 1 minus y minus 0.045. This is known as the operating line equation. So this is the operating line equation, and with this operating line equation we can obtain the following data and tabulate it. You can obtain x and y. So if you continue to put the values of x, you can be finding y. So if you put x to be 0.0, if you put x to be 0.0 and make y the subject, you will find y to be 0.0124. If you put x to be 0.0307, you find y to be 0.02. You put x to be 0.1325, you find y to be 0.05. You put x to be 0.271, you find y to be 0.10. If you put x to be 0.383, you find y to be 0.15. You put x to be 0.472, find y to be 0.2. So this is the equilibrium data, this is the operating line data that you can use in plotting the operating line. Whereas the previous data, you can use it to plot the equilibrium curve. So having done the two, so we can now plot our equilibrium curve and operating line. So we're going to use scales of 0, 0.1, 0.2, 0.3, 0.4, 0.5, and here we're going to use 0.02, 0.04, 0.06, 0.08 down to 0.20. So here is going to be y, which is mole fraction of the hydrocarbon, and here is also x, which is as well a mole fraction of the hydrocarbon. So the Y is in gaseous phase, here in the liquid phase. So if you plot the equilibrium curve, we're going to have something like this. But when we plot the operating line with the data we got, we're going to have something like this. So that's what we're going to have. So anytime we trace our Y to a given point, we can take it down to the equilibrium point and trace the corresponding value of Y equilibrium. So that is how we get our Y equilibrium. So that said, also know that 1 minus Y lim, how we find it is simply by saying 1 minus Y plus 1 minus Y equilibrium all over 2. That's how you get 1 minus Y lim. So having plotted these two, we can now make this table so that we can use graphical integration to finally solve. So we can have the table of Y equilibrium 1 minus Y 1 minus Y equilibrium 1 minus Y lim, Y equilibrium minus Y, and finally 1 minus Y lim all over 1 minus Y brackets Y equilibrium minus Y. So the values of Y are 0.0124, 0.03, 0.05, 0.08, 0.10, 0.14, 0.15, 0.18, 0.20. So if you trace it down, we are going to be getting the value of this. We trace it on the graph: 0.03, 0.0117, 0.03, 0.0475. So like that, it traces down until if you do 1 minus anything you have here, you get what is here. If you do 1 minus anything you have here, you get what is here. For this one, like I said, the formula is 1 minus Y brackets plus 1 minus Y at equilibrium all over 2. You get what is here. Then Y equilibrium minus Y, you get all that is here. Then you now put what you have here and put this one down here, you get what is here. So having gotten all this, we can now easily use the value to plot the graph of minus 1 minus Y lim. You have this already in the table: 1 minus Y bracket Y equilibrium minus Y against Y. So choosing a suitable scale where we have 0.12 and 0.2, so that we have a sketch like this. You can take this down to here, take this down to here. So you're gonna have this area, and this area is actually equal to number of stages needed. So that using Simpson's rule or Simpson's formula, we can find NOG to be equal to 4.91, and that is the answer to this. Thank you. Please hit the subscribe button. Thank you. God bless you.